The cosmos, a vast expanse, once existed in a profound state of darkness. Following the Big Bang, a period known as the Cosmic Dark Ages permeated the universe. During this epoch, only primordial hydrogen and helium gas existed, slowly cooling and expanding. Light, as we perceive it, had not yet been forged by stellar furnaces, rendering the early universe an opaque void to any hypothetical observer. Within this cosmic twilight, the first stars, designated population 3 stars, began to coalesce. These hypothetical behemoths would have been hundreds of times the Sun's mass, burning with an intensity unseen since their ultraviolet radiation would have reionized the universe, ending the Dark Ages. Observing their faint, highly redshifted light, stretched to infrared wavelengths, represents a pinnacle of astrophysical endeavor. Current astronomical observatories, whether ground-based or orbital, face immense challenges in capturing this primordial light. Traditional telescopes rely on meticulously polished glass mirrors, which become prohibitively expensive and technically complex beyond certain diameters. The sheer mass and thermal stability required for apertures several tens of meters across present a fundamental engineering barrier to deeper cosmic surveys. An alternative technology, the Liquid Mirror Telescope, offers a pathway to unprecedented aperture sizes. This innovative design utilizes a rotating dish containing a reflective liquid, typically mercury. The constant centrifugal force precisely molds the liquid surface into a perfect parabola, ideal for focusing distant light. This principle bypasses the intricate grinding and polishing of solid glass mirrors. The primary advantage of liquid mirror telescopes lies in their scalability and cost efficiency. Constructing a multi-meter liquid mirror is significantly less expensive and complex than fabricating a solid equivalent. This allows for far larger light-gathering surfaces, crucial for detecting the exceedingly faint signals from the universe's dawn. A larger aperture translates directly to greater sensitivity. However, liquid mirror telescopes possess a fundamental limitation. They can only point directly upwards at the zenith. Their parabolic shape is maintained by continuous rotation, meaning any tilt would deform the reflective surface. This constraint restricts ground-based instruments to observing only the narrow strip of sky directly overhead as Earth rotates, severely limiting their target acquisition capabilities. To circumvent this zenith-pointing restriction, proposals exist for placing liquid mirror telescopes in space. In orbit, an LMT could achieve a stable, continuous observation of a specific celestial field over extended periods. A carefully chosen orbit, potentially at a Lagrange point, would allow the telescope to drift with minimal perturbations, maximizing exposure time on targeted deep-field regions. The primary reflective surface of an orbital liquid mirror telescope would not necessarily be Mercury. Mercury presents toxicity and volatility challenges in a vacuum. Instead, ionic liquids or low-vapor pressure molten metals like gallium alloys are being investigated. These substances offer stable reflectivity and maintain their liquid state across the extreme temperature fluctuations of space, crucial for long-duration missions. Maintaining the parabolic shape in space requires precise control over the rotational speed. Microthrusters or reaction wheels would continuously adjust the rotation to counteract any minor disturbances, such as solar radiation pressure or micrometeoroid impacts. Gyroscopic stability would be paramount, ensuring the mirror's surface remains perfectly smooth, maximizing its light-gathering efficiency. An orbital liquid mirror telescope designed to detect population 3 stars would require a very large aperture, potentially 20 to 100 meters in diameter. Such a vast mirror would collect an immense amount of infrared light, even from sources at extreme cosmological distances. Its sheer light-gathering power would compensate for the extreme faintness and redshift of the earliest stellar emissions, pushing the boundaries of observable cosmology. The detection system for such an instrument would consist of highly sensitive infrared detectors, cryogenically cooled to near absolute zero. This extreme cooling minimizes thermal noise, allowing the faint redshifted infrared photons from the early universe to be distinguished from background radiation. Advanced signal processing algorithms would then sift through the data, searching for the unique spectral signatures of primordial stars. The target signal, light from population 3 stars, is not just faint, but also stretched by the universe's expansion into the infrared spectrum. This extreme redshift, where visible light is elongated into much longer wavelengths, is the primary indicator of immense cosmic distance and age. The LMT's design, optimized for infrared detection, would specifically be tuned to capture these elusive ancient photons. Beyond simply detecting these stars, the telescope would analyze their spectral composition. Population 3 stars are theorized to have formed exclusively from hydrogen and helium, the only elements present after the Big Bang. Their spectra would therefore lack heavier elements known as metals in astrophysics. Identifying this metal-free signature would be definitive proof of their primordial nature, a groundbreaking discovery. The operational sequence for an orbital LMT would involve months, perhaps years, of continuous observation on specific deep-field targets. Unlike terrestrial telescopes that contend with atmospheric interference and diurnal cycles, a space-based LMT could accumulate photons uninterrupted. This extended integration time is essential for building up enough signal from such incredibly distant and faint cosmic objects, slowly revealing the universe's initial illumination. Data transmission would occur via high-bandwidth laser communication systems, beaming vast quantities of raw spectral and imaging data back to Earth. Sophisticated algorithms on ground stations would then process these datasets, correcting for instrumental artifacts and atmospheric effects for any secondary observations. This constant stream of information would allow for the gradual reconstruction of the early universe's stellar landscape. The logistical challenge of deploying such a colossal instrument in space is immense. Launching a large quantity of liquid and the necessary structural components into orbit requires multiple heavy-lift rocket launches. Once in space, robotic assembly mechanisms would meticulously construct the large dish, fill it with the reflective liquid, and initiate its precise rotation. This entire process demands unprecedented precision and automation. Furthermore, ensuring the long-term stability and integrity of the liquid mirror in the harsh space environment poses significant engineering hurdles. Protection from micrometeoroids and space debris is critical. Even a small impact could disrupt the mirror's perfect parabolic shape. Redundant systems for rotation control, temperature regulation, and liquid replenishment would be vital for a mission spanning decades. A crucial aspect of orbital LMT design involves vibration isolation. Any minute vibration from internal spacecraft operations or external perturbations could ripple across the liquid surface, distorting the optical path. Advanced damping systems and active vibration suppression technologies would be integrated into the structural framework, ensuring the liquid mirror remains an exquisitely smooth and stable observational platform for precise imaging. Thermal management is another complex system requirement. The reflective liquid must be maintained within a precise temperature range to preserve its viscosity and reflectivity. Heaters would prevent freezing, while radiators would dissipate excess heat generated by onboard electronics or solar absorption. An optimal thermal environment ensures the liquid behaves as intended, maintaining its optical quality for accurate measurements. The entire system must operate autonomously for extended periods. Ground control would primarily monitor health and status, upload observation schedules, and download scientific data. Onboard AI would manage routine operations, troubleshoot minor anomalies, and optimize observational parameters. This autonomy reduces the need for constant human intervention, maximizing scientific uptime and efficiency. Beyond the primary mirror, the focal plane instrumentation is a complex system in itself. It would incorporate adaptive optics, even in space, to correct for any residual aberrations caused by slight mirror deformations or thermal gradients. This ensures the collected photons are focused into the sharpest possible image or spectrum, critical for distinguishing faint, distant sources from the background noise. The power supply for such a large orbital observatory would demand massive solar arrays, efficiently capturing sunlight to feed its myriad systems. Energy storage and advanced batteries would ensure continuous operation during eclipses. Redundant power distribution networks would route electricity to propulsion, thermal control, data processing, and scientific instruments, ensuring uninterrupted functionality in deep space. The data processing pipeline, from raw photon detection to analyzed scientific results, is a sophisticated multi-stage system. Onboard processors would perform initial data calibration and compression before transmission. Terrestrial supercomputers would then handle the complex task of stacking immense quantities of exposure data, performing sophisticated spectral analysis, and ultimately extracting the faint signals from the universe's earliest epochs. Compared to traditional solid mirror telescopes like Hubble or James Webb, Orbital LMTs offer a distinct advantage in sheer aperture size. While Webb achieved a 6.5-meter primary mirror through complex folding, an LMT could theoretically reach diameters of 50 meters or more. This vast light-collecting area provides an unparalleled photon-gathering capability, crucial for probing the dimmest objects at the edge of the observable universe with precision. However, traditional telescopes offer superior pointing flexibility and multi-wavelength observation. A solid mirror can be precisely steered to any celestial target and often incorporates instrumentation for a broader range of electromagnetic spectra, from ultraviolet to mid-infrared. The LMT, by contrast, is primarily an infrared collector for deep-field surveys, inherently less versatile in its observational scope and agility compared to its solid counterparts. The operational lifetime of an orbital LMT poses another contrast. While solid mirrors are static, the liquid surface requires continuous management. Contamination from space dust or degradation of the reflective liquid over decades could necessitate in situ maintenance or even fluid replacement. This contrasts with the inherent structural stability of a solid mirror, which primarily degrades from micrometeoroid impacts or instrument obsolescence. Terrestrial LMTs face significant atmospheric limitations. Earth's atmosphere absorbs most infrared light and causes scintillation, blurring images. Space-based LMTs completely bypass these issues, allowing for crisp, continuous observations of highly redshifted light. This environmental advantage is paramount for detecting the faint, stretched light of population 3 stars, which would be almost entirely obscured from the ground. The very nature of light from the first stars, extremely faint and redshifted into the infrared, necessitates instruments optimized for this specific signature. While general-purpose observatories have their place, the Liquid Mirror Telescope's design represents a specialized tool, a cosmic magnifying glass designed to peer through billions of years of cosmic expansion to glimpse the universe's nascent luminosity. Consider the limitations. Should the rotational system fail, even temporarily, the liquid surface would deform, instantly rendering the mirror useless. A complete system reboot and restabilization would be required, potentially losing critical observation time. This fragility contrasts with solid mirrors, where minor mechanical issues might degrade image quality but rarely cause complete operational cessation, emphasizing design redundancy. The reflective liquid itself represents a point of vulnerability. Over vast timescales, some evaporation, even of low vapor pressure liquids, is inevitable in a vacuum. A replenishment system, perhaps involving on-orbit storage or even in situ resource utilization, would be crucial for mission longevity. Without it, the mirror would slowly thin, losing its uniform reflective properties and ultimately ceasing to function as an optical instrument. Micrometeoroid impacts, though rare, could prove catastrophic. A sufficiently large particle striking the liquid surface could introduce permanent ripples, contaminants, or even puncture the containment vessel. While protective shielding would mitigate smaller threats, a significant impact could compromise the mirror's parabolic integrity, leading to an irreversible degradation of image quality and potentially ending the scientific mission entirely. The operational lifespan of such an advanced observatory is intrinsically limited by technological obsolescence. As detector technology advances or new observational paradigms emerge, even a perfectly functional LMT could be surpassed by newer, more agile instruments. Upgradability in deep space remains a complex challenge, making the mission's ultimate scientific yield a race against the relentless pace of innovation and discovery. Furthermore, the immense financial investment required for an orbital liquid mirror telescope makes it vulnerable to shifts in political will and scientific funding priorities. A mission of this scale demands sustained international collaboration and resources over decades, from conceptual design to operational decommissioning. Any significant reduction in support could halt its development or curtail its operational life, leaving its grand potential unfulfilled. Unforeseen technical challenges inherent in any groundbreaking space mission could also lead to project collapse. A critical component failure during deployment, an unanticipated interaction between the liquid and the space environment, or fundamental flaws in the rotation mechanism could render the entire effort futile. The vacuum of space is an unforgiving proving ground for even the most rigorously tested designs, demanding robust engineering foresight. Should these engineering and logistical hurdles be overcome, the revelation promised by Orbital Liquid Mirror Telescopes transcends mere data. to witness the light from the universe's initial stars, objects that first ionized the cosmos and forged the first heavy elements, is to gaze upon creation itself. It is a direct observation of the universe's formative moments, a cosmic genesis unfolding across billions of light-years of spacetime. The faint, stretched photons journeying across vast expanses of expanding space would carry the primordial signature of a universe devoid of galaxies and complex structures. They would be echoes of an epoch when space was illuminated not by the familiar light of countless stars, but by the isolated, gargantuan bursts of thermonuclear fusion from solitary, supermassive population 3 giants, fundamentally altering the cosmic landscape. The successful deployment and operation of an orbital liquid mirror telescope would redefine humanity's understanding of cosmic evolution, providing tangible evidence of the universe's earliest epochs. It would reveal the initial conditions that seeded the galaxies, stars, and ultimately, life itself. What other fundamental mysteries of the universe await our discovery, just beyond the reach of current observational technology, necessitating such bold leaps in engineering?